All right, good morning, guys. Welcome to class this Wednesday. I don't know if you guys know this is the start of the fourth week in this class already. I find that hard to believe, but anyway, we're well on our way into the semester here. Hopefully all your other classes are going well. Quick Go USA. Any soccer fans in here? Yeah, there we go. A big win last night. And then I guess Honduras helped us out, and we're going to the World Cup, so I'm really excited about that. A few quick announcements. Homework 2 is due tomorrow. If you'll note on Carmen that chapter 3, number 26 was listed again, and that was on your first homework assignment, so no need to do it twice. If you did, I guess that's all right, but you can scratch that one off the list. There's only going to be 7 problems for this assignment. A few other notes. Again, as I sent you some emails, we're going to be using new notes from now on, so hopefully you guys brought those with us. Apologize for making you print off chapter 5 and 6 twice. There was a little disorganization as we got the semester started, and the notes that we had been using were ones that I'd used from previous semester, and I wanted to just give you guys some notes so you'd have a batch to print off. We'll be switching over to use the same notes now as the other 2 sections of this class. So those notes I think will be posted weekly, so they might not be as many posted at once for you to print out all at once. So hopefully that's not too big a problem. And one other announcement, I mentioned this in the email yesterday, there was an error with my little recording from on Friday, and thank you to one of your classmates for bringing that up. And just to note that if you are noticing any issues with those videos, please let me know, and I'll see what I can do about that. Yeah. Thank you. That was the other announcement that I was going to make and forgot. There's a data. So for number 44 here, it was also brought to my attention. Thank you again. That the data set that was posted on Carmen is different than what's in the book, and so please go ahead and use the data set that's in Carmen, so you can use technology. Again, if you did do that by hand or something, just make a note by that. I don't know why there was a discrepancy, but go ahead and use the data set from Carmen. It'll make your life a little easier. That's fine too. Yeah. Again, if you did something different than what's with the data set, just make a note. Just make a note of that on your homework, and that'll be fine. Any other questions? Any other concerns? How are things going? You all good? If we have any Imgur or Reddit people out there, someone put a really funny set of pictures on the back channel that I will unfortunately not make time for now, but I'd recommend checking it out. Anyway, okay, we're going to start with chapter 5 today, and title here is Regression. So hopefully you have those notes in front of you and ready to go. Just drawing a quick connection between, there's a very good reason why we did chapter 4 and then immediately following did chapter 5 here, and that's we're going to kind of take what we talked about in chapter 4 one step further. So Chapter 4, we were talking about correlation and scatter plots, and again, we found that those are helpful in visualizing and describing strength, direction, form, all those kind of things of a relationship between 2 variables. So showing the strength and direction of a linear relationship, remember that's kind of what we're focusing on here, between 2 quantitative variables. So as a motivating example for what we're going to do next, there in your notes you have some data, and the data here is, the example here is comparing the amount of time that students spend studying for an exam and the score that they get on that exam. So this is not meant to make you feel guilty about studying for your exams, but anyway, here we go. So what you have there is again the number of hours that a student spends studying on the exam and the score that they get. And kind of basic info here is that you guys as students, of course, only have a certain amount of time that you can study. And so suppose that you have 3 hours you can study on Saturday, 3 hours on Sunday, maybe you have an exam next week, and then think about what kind of grade could you expect here from this. So again, we have some data. Let's make a scatter plot. And to kind of review what we talked about on Friday, let's quickly think about look at the first question there, which says what seems to be the direction, strength, and form of the relationship. So who can help me out with some of these things? Positive linear? Okay, yeah. So again, I think maybe something that's helpful for me anyway when I'm looking at scatter plots is kind of put some lines on the actual scatter plot to kind of show you the general general direction of what's happening. So we kind of have this kind of a shape going on here. So that's definitely positive and linear. So there's a positive linear relationship here between hours studied and the score you get on an exam. What about the strength? Anybody help me out there? Very strong, right? It's a very strong relationship. And I think later we'll see what the correlation is, and again the correlation is pretty high. Very high, yes. So exactly, that's a very strong relationship. So kind of as an intuitive thing here, using this scatter plot, kind of looking at the entire data set, assuming that you studied 6 hours, what kind of a grade would you expect if you studied for 6 hours, based on just looking at the scatter plot, just kind of taking a wild guess? $70 to $80 range. Why do you say that? Okay, yeah. So if I come down here to where my number of hours spent studying is, and I kind of draw a line straight up. So if I kind of go straight up from here. Again, the point is that kind of the data is falling right in between there, 70 and 80. So maybe something in this range, kind of picking out the right in the middle of that. That's exactly right. So you could say 70 to 80, or maybe a little bit lower, maybe a little bit higher than that, based on what you pick out here from the scatter plot. But anyway, the key idea here is that kind of looking at all the data, using this data to answer this question, pick out the number of hours that we spent studying, and kind of see where that corresponds with the rest of the information on the scatter plot. So that's kind of the basic idea of what we're going to be looking at here. But we can formalize this a little bit more. We don't have to just say it's about 70 to 80 or something like that. So the goal for this chapter is we're going to try to create an equation that best quantifies that relationship that we see in the scatter plot. So again, we have a linear relationship that we're trying to talk about, and then we're talking about that relationship between, remember, a response and an explanatory variable. And so when we're looking at the scatter plot, we want to have an equation that we can plug something into instead of just kind of guessing to say here's about where we are. So keep that's kind of our goal in mind here, and this leads us to the notion of what's called a regression line. So let me fill in these things here for you. So a regression line is a straight line. Remember, we're talking about a linear relationship, so it's going to be a straight line that describes how a response variable y changes as the explanatory variable x also changes. So again, a regression line is a straight line that describes how a response variable y, we're going to use y to denote our response variable, kind of we plotted that on the y-axis, talk about how that changes based on how an explanatory variable x changes. So that thing we plot on the x-axis is going to be our explanatory variable. And we will often use a regression line here to kind of what we were just doing sort of informally there. We want to predict the value of y for a given x. So again, we're going to use a regression line to predict the value of our response variable y based on whatever we're kind of interested in as far as the x variable goes. So if you think about it, that's exactly what we just did on the scatter plot. We took a particular value of x, our explanatory variable, and we predicted the value of y. So we took a value of a number of hours, if we study a number of hours, and then we predicted or guessed what the value of y would be, or what our exam score would be. So again, just formalizing that sort of ad hoc procedure we did just a minute ago. Okay, so again, this regression line has a derivation that has sort of a mathematical motivations we're not going to spend a whole lot of time talking about, but formal definition here is that this regression line, or this least squares regression line, is the line that minimizes the sum of the squared vertical deviations between the data points and the line. So you don't need to worry about this too much, but let me kind of show you where we're getting this line. So that red line there is the line we're shooting for. And what it's doing is it's taking each point, and we're calculating the distance from the point down to the red line. So this is that's one deviation, and we can go to our other points. For this point here, we can see that one is below the regression line. So if you took all those differences, squared them, added them up, what you can take my word for is that this red line here is the one that, out of all the lines that are possible, is the one that minimizes those distances. Again, you don't need to really worry about that, but kind of that's where this line is coming from. That's how we're calculating it anyway here. Okay, so let's talk about our equation. Remember, our goal here is to create an equation for this line. So the least squares regression line, again, is going to have this equation: y hat equals a plus bx. So this is we're going to call this y hat because it has a little hat sitting on top of it, and then we're going to use equals a plus bx. So I'm sure from your algebra classes you've maybe seen before something like y equals mx plus b. Then does that sound familiar to anybody? That's sort of a classic way of labeling things for algebra. So same idea here. We're just going to change the notation a little bit. So we're not going to use that. Instead, we're going to use y equals a plus bx. And we'll put a little hat on the y, which I'll talk more about here in a second. But anyway, same idea. We're just kind of calling what was b before is now a, and what is, maybe you're familiar with, m is now we're calling that b. So here what y hat is the predicted value. And I'll tell you a little bit more about what I mean by a predicted value there. Or I guess we can just say, remember, our goal here is to, for a particular value of x, whatever our explanatory variable is there, we want to predict the value of our response, or the y variable. And so because it's a predicted value, we're going to put a little hat on it to kind of denote the fact that it's not something we actually observed. It's something that we're predicting or guessing. And then, just like you've seen before, a is the intercept. That's what we'll call a. B is the slope, and then just note on some units that we have going on there, just to keep that straight. So again, same kind of terminology that you've probably seen before. We're just labeling things a little bit differently. Any questions you guys can think of on this formula, where it's coming from, what it means? Okay, let's push on then. So to find, so again, if you look back at the scatter plot here, again the red line there that's the red line that we have found. So this line is y hat equals a plus bx. And so the question now is, how do we figure out what a and b are? So again, if you know from your previous studies that if we know the slope and the intercept, we know what the line is. We know the formula for the line. So now we need to find what those two things are. So the first thing we can do is calculate the slope, which we're calling that b. So the first thing we want to do that, and here's our formula for it. So again, we're using summary statistics to calculate what that slope is, and that's simply going to be the correlation r, and then times the ratio of the standard deviations. So we have the standard deviation of our y variable, and we have the standard deviation of the x variable, and we're just that's what our formula is. And after we have b calculated, after we have the slope calculated, we can calculate the intercept, which we're calling a, by simply using the value of b that we calculated, as well as the sample means from y and the mean from x. So using y bar and x bar, which is just the mean of the y variable and the mean of the x variable. So again, we're going to kind of skip over how we actually got this, but you can just keep in mind that, remember, this line is the one that makes all those squared distances the smallest. If that's helpful for you. So let's go ahead and, for our example with the exam study hours and the exam scores, let's figure out what a couple of these things are. So again, we're looking at these equations. We need the correlation, we need the standard deviations, the means. Again, we're not going to do that by hand. We're going to look at technology to help us out with that, and we can then calculate what these things are. So again, here I've put in your notes there a little list of summary statistics from our data. So for our exam score, that's our y variable. We also have something for our x variable, which is the hours spent. So we have the mean and standard deviation, and then we also list the correlation between those two things right there. So if we want to figure out what b is for our regression line, we can just plug these things in here. So this is equal to the correlation 0.9378 times the standard deviation of y, which again is our exam score, so that's going to be 18.706, and we're going to divide that by our standard deviation of x, which is 2.399. And if you plug that into your calculator, you can get that is equal to 7.31. So again, that's going to be the slope of our least squares regression line here. So next, once I have my b calculated, I can figure out what a is. So now I can plug in the mean of y, so that's 69.92. And I'm going to subtract off b, which is 7.31, times the mean of x, which is 4.615. And again, if you plug that into your calculator, you'll get out that that is equal to 35.88. Yes. Sorry about that little typo there. 69.62. Sorry. Thank you. That's my mean of the y. I can't read this morning. So then once we've calculated a and b, we can now just plug those into our equation. And we know that our regression line is y hat equals 35a plus bx, so 35.88 plus 7.31 x. So we're going to leave x as an unknown there. So for this data set, we want to know what our least squares regression line is. Well, there it is. And again, that is the, I sort of jumped ahead, but I had already plotted on the scatter plot that we looked at just a minute ago that had the red line on it. That is the line that's plotted there. So let's go back and fill that in. So we now know what this line is. It's 35 point plus 7.31 x. So that is the formula for that line there. That's that red line that's showing up on the scatter plot. Okay, so next let's talk a little bit about, or I guess first of all, any question you guys can think of before I move on. Kind of what we're doing here. Does this feel okay? for now. Just taking summary statistics, my standard deviation, my means, correlation, and using our formulas to calculate what these things are. Okay. So the next thing that we always do in this class is talk about a little interpretation. So again, we can do the math, we can find out what A and B are, but now we want to be able to say what they mean in the context of the problem. So again, we have A and B. We want to say a little bit about what both of those things are. So if we want to interpret the slope of the model in context, this is B, and this is going to be just like what the interpretation was for the slope before. We can just kind of, since we know what x and y are, we can say what those are and give a good interpretation. This is and what I'm going to write up here is a good template, so you're definitely going to have to do this in the future, homework problems, exams, and I would kind of advise that you follow this sort of template. So what this means, here the slope of B equals 7.31 tells us that, and this is kind of an on average. Exam scores increase by 7.31 for each additional hour of studying. So again, the slope here is telling me the slope B equals 7.31 is telling us that sort of on average for this data set, exam scores, our y variable, will increase by 7.31 for each additional hour of studying. So as you study, so if you go from studying 5 hours to 6 hours, your exam score on average will increase by 7.31. If you go another hour, so again, you can kind of think of this as the rise over run situation. So if I have 5, 6, and 7 here, my line is kind of going like this. So as I go from here to here, if I move 1 unit over, I'm going up 7.31 units there. If I go over 1 unit here, I'm going up another 7.31. So as each unit that I increase in my x variable, I'm going to increase the y by 7.31. Again, that's sort of the usual interpretation of slope that you've seen in algebra before. Nothing different. I'm just labeling what x and y are. So like I said, this is a good template to follow. So the slope tells us that on average, and then here you'll fill in your x variable, and then increase by whatever b is for each additional unit of the the y variable increases by whatever b is for each additional unit of x. So you can kind of use this as a sort of a template to answer this type of a question for other examples. Any questions you guys can think of on the interpretation here for B? Yeah, so what would the units of B be? Of B? Okay, yeah. So jumping back here, so B is in units of y divided by units of x. So here B would be in exam points on your exam grade divided by hours studying. So no, you don't worry about labeling that. So that is technically what the units are. That doesn't really make any sense though, right? So it's hard to think of what exam grade per hour of studying means. It's not as clear. So yeah, don't worry about labeling B. This interpretation is kind of saying what it means. Yeah, good question. All right, so we talked about B. Let's talk about the intercept, the other thing going on here. And again, I'll recommend this is a good way to say what this is. The intercept A which we found to be 35.88, tells us that the exam score for a student who studies 0 hours is about 35.88. So again, the intercept A equals 35.88 tells us that the exam for a student who doesn't study at all, who studies for 0 hours, is 35.88. So again, that's kind of like what you've seen before, right? The intercept, you know, that's just the place where the line crosses the y-axis, right? The y-intercept. And so that just means that when x equals 0, that's the exam score that you can expect. Just a note that there will be some cases where the x variable can't equal 0, or it doesn't make sense to think about the x variable equaling 0. I'm not sure if we'll have an example of that here in class. I might get to that, but just keep in mind that it doesn't always make sense for x to equal 0. If you're talking about, if you're trying to predict, I don't know, how much you weigh off of how tall you are, it doesn't make sense to talk about being 0 inches tall. So keep in mind that this might not always, having the explanatory variable equal to 0 might not always make sense. So let me just write that down. So again, just talking about the explanatory variable, or our x variable equaling 0, doesn't always make sense. But even when that's the case, this is an okay way to interpret what that intercept is. So stick with that interpretation, but again, just keep in mind it doesn't always make sense. So a question just came in: can the y-intercept be negative? Absolutely, yes, it can. As can the slope. So either the slope or the intercept can both be negative. Absolutely. So again, maybe just a little teaser for what's to come here. Again, we have a positive relationship here, right? So our slope is going to be positive. If you have a negative relationship, your slope will be negative. And it could certainly be the case that your y-intercept is less than 0 as well. That's totally okay. Great question. Okay, so as usual in this class, we kind of talk through what our formulas are, the actual equations for things, do an example of that. But good news is we're not actually going to require you to do these calculations all the time. Again, we're going to rely on technology to help us out. Again, it's important to know what these things are and what they mean, where they come from. But we're going to go ahead and use technology to calculate these things. We got a nice mower going out there, huh? All right, so this table right here is something that I can get out of JUMP, and I'll leave it to your recitation leader to demo how to do this, how to get this information. But everything that we just calculated we can find from this table right here as well, with kind of skipping over those actual steps that we did. So keeping an eye on that little table of information. Oh, there it is. Still have it there. My question here is, based on the JUMP output, what is the equation of the least squares line? Well, you can kind of pick those out from right over here. So you're going to focus in on this column right there, and don't worry about this stuff. That's kind of beyond what we'll talk about in this class. If you want to know what that is, take more stats or come talk to me. So again, if I'm looking at this output right here, I can just pick out what my A and B are. So again, my intercept right there is 35.868, which is about the same. My hours spent studying is right there as well. So from this output, I can just straight up write down what this is. This is 35.86. Let's round it up to 9 plus 7.311. Yeah, 312x. So again, it should be pretty straightforward picking that stuff out of jump, but so the 7.31 is attached to the x variable, which we know up here. This is our x variable. The hours spent studying, that's our x variable. So go to that line to figure out what's your slope, what b is, and then the other line is going to be your intercept. Any questions you guys can think of on this one? So a question just came in, will we have access to jump during exams? And the answer is no, but what we'll do in the exams is we'll give you output like this and ask you to pick out the right things and kind of interpret the output from technology. So you won't need to use jump, you won't have access to, I mean, it'll be a written exam, it's not on the computer. So you won't have jump, but again, we'll give you the output and ask you to interpret that output and pick out the right things there. Good question. All right, so if you remember what our goal was, if you look back to that first page of your notes, our goal is to create an equation, again, that best quantifies the relationship between these two variables. But then we also want to use those to make predictions, right? So kind of like that first example we talked about, we can now use this to say some interesting things here about this example. So again, let's go ahead and use our regression line to make some equations. So if, again, thinking about that same question, if I study 6 hours, what can I sort of expect my exam score to be? That's kind of like predicting what my exam score is going to be based on studying 6 hours. So before we said, oh, it's between 70 and 80, kind of somewhere in that range. And now we can now say a little more clearly what we have here. So again, we're going to use our regression line. So we're going to write this out. Y hat, our predicted exam score is going to equal A plus B x, where x is the number of hours that I'm studying. So based on a certain number of hours studying, what can I expect my exam score to be? And we can now plug these things in. My intercept was 35.88 plus 7.31 x. Where now I'm interested in x equaling 6. So let's plug x equals 6 in there. And then I can calculate out what that is. That's going to be equals to 79.7. So again, if I study 6 hours, what I'm predicting here is that my score would be 79.7. Okay with what we're doing here? Oh, let's do one more example. So if we want to think about, so what if I only study 4 hours? What could I sort of expect my exam score to be? Again, my y hat, my predicted exam score is again 35.88 plus 7.31x. Now I want to see about studying 4 hours, so x is going to be equal to 4. So 35.88 plus 7.31 times 4. And if you calculate out what that is, that's going to be about 65.1. So thank you. Someone's keeping me honest on here. So the question just came in, would we say that as a percent? So 79% is the score, or do we just leave it without units? I definitely should be writing units on here. So let's go ahead and put a points there. 65.1 points. Which you guys all know means that you had a 65% on the exam. That's kind of what we're talking about here. But we'll leave that in the points units. Let me go back and fill that in. It is important to put units. Thank you, keeping me honest. Any other questions you guys can think of on predicting here? So whatever my number of hours is that I'm if I'm expecting to study 5 hours for this thing, I could plug 5 into there to figure out what my sort of expected exam score was. If I wanted to study for 7 hours, 8 hours, 1 hour, whatever that was, I could use this to sort of guess what my exam score would be. That's kind of the idea. We're using this to predict a certain value of y for a certain value of x. So let's think about some properties here of this least-squares regression line. First and foremost, it is very important to make sure we have our x and y variables in the correct place. So it is very important that we know which variable is our explanatory variable, which is our response variable. Because if you reverse those two roles, you'll get a different answer. Your A and B will be different, and you'll get sort of the wrong answer. Question came in as well. Is there a rule of thumb on decimal places? Not necessarily. Do a couple. Again, make sure to round at the end of your calculations when it comes to decimal points, and then put 1 to 2 to 3, something like that is fine. And one more question. So then on the exam, are we going to need to use the equations to figure out a B, or we just use jump outputs? Again, you can just use jump output for the exam, for your homework, for whatever. Unless one of the homework questions specifically asks you to calculate it using the formula, you can always use jump. Okay, thank you for those questions. So again, it is important to keep our x and y variables straight when we're doing these calculations. Secondly, there is a close connection between the correlation and the slope of the least squares regression line. So this is getting at that thing I was hinting at just a minute ago. The slope and the correlation, we can say they always have the same sign. And so if you remember what the equation for the slope was, it was b equals r times the standard deviation of y divided by the standard deviation of x. What can we say about the sign of the standard deviations? Are those going to be positive or negative? And everybody said a little loud. Positive, right. Remember, the standard deviation is measuring spread, and you can't have a negative spread. So the standard deviations will always, s sub y and s sub x will always be positive. So whatever sign r is, if the correlation is positive, b will be positive. If the correlation is negative, b will be negative. So they will always have the same sign. A few more facts here. That the least squares regression line always passes through the point x bar y bar on the graph of y against x. And let me maybe jump back here and just show you that. So if I erase these things here. Again, from our summary statistics, let me see, the mean of x was 4.6. So maybe like here was our x bar. The mean of y was 69.62, so about here. This is our y bar, and if we trace this over, you can see that the regression line passes right through that point. So this is a very visual argument, but that will always be true. And finally, let's say something about the correlation here. So the correlation, again, remember, describes the strength of a linear relationship. So remember, the correlation we're talking about, remember, when we're looking at scatter plots, the relationship could be nonlinear, and that's fine. That's fine to talk about. But that the correlation will not capture that relationship. It will not tell you anything about a nonlinear relationship. So we take the square of the correlation, r squared. This has a very specific interpretation as well here. So this is the fraction of the variation in the values of y that is explained by the least-squares regression of y on x. So again, if we square the correlation, that's going to be r squared. Again, the formal interpretation here is that it explains that is the fraction of the variation in the values of y, so whatever our response variable is, that is explained by the least squares regression of y on x. So that makes perfect sense, right? You know exactly what that means? Of course not. That's really a little confusing. So let's apply this in our example here, and maybe I'll tell you a little bit what I mean by this. So again, calculating r squared, and then interpret that in context of this example. And this is again something that you will have to do on homework and exams. So this is a good way to talk about this. So r squared, again, we can just take the correlation and square it. So our correlation is 0.9378. If we square that, we will get 0.8795. Or 87.95%. All right, so now let's say, using that definition on the previous page, let's say what that means here. So what this means is that about 87.95% of the variation in exam scores, which is our y variable, is explained by this regression line. So that is explained by the x variable. So explained by the number of hours studied. So again, now we can interpret r squared here, the square of the correlation, that is about 88% of the variation in our exam scores, and our y variable is explained by this relationship with hours studied, by the number of hours studied. And then so what about that other 12% there that we have? So we can just say the other 12% of variation is not explained by the regression line. So this again is my interpretation for what the square of the correlation is, and it's telling us how much variation in y is explained by this relationship. Any questions you guys can think of on this? Yeah, so let's talk about the difference between r and r squared. Well, so my r squared is just taking the correlation and squaring that. So r, the correlation just describes, remember back to chapter 4 on Friday, the correlation describes the strength of the linear relationship between two variables. And we talked about lots of properties there. We had a formula for that and everything. Again, but r close to plus or minus 1 means we have a very strong relationship. As it gets closer to 0, that means we have almost no linear relationship, right? So r squared is, again, just taking the correlation and squaring it for these in this context. Tells us the percentage of variation that's explained by our regression line. So I know I'm probably just saying that again, so if we look back to the scatter plot, maybe that's a good way to look at this. Keep jumping around here. So over here on my, again, if I look just at my exam scores, my y variable, I have what each of these values are right there. I have 40, I have a 50, so I have all these points over here, and I could calculate the sort of the variation in that. So I have a certain amount of spread in just that y variable, thinking about just that y variable by itself. And what I'm saying by r squared is the percentage I'm talking about there is how much of that variation is explained by using this regression line. So how much of the variation in that y variable I've explained or sort of accounted for with this relationship with the hours studied.
So R is how strong the line is, and R squared is like how much of the data falls in that line.
That's pretty good. So the correlation R is sort of how strong is the relationship, and the R squared is sort of how closely, you can think about it as being how closely do these points lie to this line. So I have a certain amount of variation in all of the y, and then again, a higher R squared means the points are falling closer to that line. It's kind of a better relationship. That's good. This is really tricky. So if this is confusing to you, don't worry about that. I mean, that's sort of expected. Yeah.
Is there like a value at which R squared is so low that you're like, well, this actually doesn't help us out? You know what I mean?
Oh yeah. So the question was, is there a value of R squared at which if it's so low that we can say sort of it doesn't help us? Definitely yes. So again, since do I say anything about this? So again, the correlation R is between -1 and +1. And that means that R squared is between 0 and 1, or 0% and right. So if correlation between -1 and +1, that means that R squared will be between 0 and 1. And the question you're asking is sort of is a very good one. So if you see a strong linear relationship in the plot, or I guess for a regression line, would you want R squared to be really big or really small? Big, right. So if R squared is large, is close to 1, that means that there's a very strong relationship in it, and that means that you have a very high percentage of the variation that's being explained by the regression line. However, if R squared is really small, if R squared is close to 0 or 5% or 10%, then that's kind of bad. That means that the regression line isn't really going to help you. So as we will discuss, the R squared is a great way to sort of evaluate or assess is this regression line any good. So if R squared is close to 1, that means you have a really good regression line. If R squared is close to 0, you have a really bad regression line. As far as a specific point of is there a cutoff at which you can sort of say, here the line is good, here it's bad? It definitely depends on the context. So if you're in sort of a scientific experiment, you want R squared to be really high. If you're in more of a social sciences setting, If r squared is a little lower, that's still okay. So there's not an exact cutoff at which you can say it's really, really bad or good, but yeah, great question. Question, are we going to be tested on how to calculate r squared in the exam? Yes, maybe. Although I think that's included on the jump output. I'm not exactly sure about that. But in any case, knowing that it just simply is taking the correlation, whatever that is, and squaring it.
But we don't need to know how to calculate r.
But you do not need to know how to calculate r. That is correct. Yeah, you will not be asked to calculate the correlation by hand. That would be terrible. So that will be, you can get that off of, that will always be given to you in jump if you need to say what it is. But you might be asked to pick it out at the output, which should be pretty straightforward.
Are we going to be given formulas?
Pardon?
For any of these equations?
Are you going to be given formulas? I believe that you will be allowed to bring a note sheet to the exam. I'm not entirely sure of Dr. Baker's call on that, but I think that will be true. Sorry about the yes, maybe response there. All right, well, let's talk about one more quick thing here before we finish up for today. Let's talk about the idea of residuals. So this is another thing that we're going to be discussing here. So a residual is the difference between an observed value of the response variable and the predicted value and the value predicted, I guess we'll say, by the regression line. So a residual, simply we're taking the difference between something we've observed and something that we have predicted. And so there's kind of written out in words what that means. So we're going to take the observed y minus the predicted y. So that's why we're using y hat. I don't know if that seems confusing to you, but we're using y hat just to note that that's a predicted value as opposed to something we've actually observed. And you can kind of think of the residual as sort of an error. So again, we make a prediction, and we can compare that to what was actually observed, and we kind of see how far off we were. That's kind of what we mean by a residual here. So we can actually do this for a few of our... So again, in this example, we predicted what my exam score would be if I studied for 6 hours. But if you look at the data, there are actually two students in that data set that did study for 6 hours. So let's talk about the residual for each one of those. Again, my predicted y was 35.88 plus 7.31 times 6, and that was 79.7. Okay, so there was one student who studied for 6 hours, and they got a 68%, 68. So the residual here for this student is equal to the observed value, 68, minus 79.7, the predicted value, negative 11.7. So residual for this student. Another student studied for 6 hours. 6 hours translated into a 93. So the residual for this student, again taking the observed value minus the expected value, the observed value, minus the predicted value, take the observed value 93 minus what I predicted for that student, 79.7, and their residual is 13.3. So again, this is the observed values minus predicted. Does sign matter? Absolutely, yes, it matters. So you always want to take the observed value minus the predicted value. If you did it the other way around, you would get the opposite sign. So make sure to take the observed minus the predicted and not the other way around. So the sign is very important here.
So like what's the difference between negative and positive?
So what's the difference between negative and positive here? So let's take this student here. So their residual is negative 11.7. So that means that you can see it here. If a negative residual means they scored, did they score lower or higher on the exam than we expected them to? Lower, right? So their actual score was 68, and we guessed that they would get a 79.7. So we overestimated their score. So negative residual means that the observed value is less than what we predicted.
So if we're asked to like look at that, we would just say like instead of they were 11.7 points away, we would say they scored lower. However.
Yes, exactly. So it is important which direction away from the prediction they are. Yeah, great question. So we overestimated theirs. For the other student, we guessed that they would get about an 80%, and they got a 93. So they sort of overperformed. We sort of underestimated that student. So yeah, so the sign is important. All right, I'm out of time, guys. Sorry I kept you a few seconds over. We'll pick this up on Friday. Until then, have a good rest of the day.